Hello, this is Mr. Henry, and this is lesson 3.3, Sequence of Transformations. The essential question says, how do I represent similar figures using a sequence of transformations? So this lesson and into the next bunch, the rest of this module, are all talking about similar figures. That is one of the other major topics in 8th grade math. So we have Pythagorean theorem as a major one. We have similar figures. We also have lines, scatter plots, functions. So you're going to see the rest of this module is devoted to these similar figures. The warm-up question says, what questions do you still have about rotations, reflections, translations, or dilations? Now, obviously, I can't answer any of those questions for you right now, but think about some of the questions you might have. Those are things you might need to take some time, either look up, or if it's something we talked about in one of the previous videos, going back and watching the video. So that's not really a discussion question we can have. Vocabulary, look at that. Nothing. We don't have any new vocabulary for this lesson. We're using the same vocabulary as the last lessons and the ones before that. So let's get right down to it. In this first section, what it asks us to do is, in each figure, describe the transformations that exhibit congruence or similarity between them. Okay, so between these two figures, the A, B, C, and the A prime, B prime, C prime, we need to figure out what series of transformations took place. So there might have been two different transformations. For example, if you would imagine, I could have taken this and I could have enlarged it if I use the scale factor or dilation, and then taking that enlarged image and moving it over there. That could be one of the transformations that took place. Maybe it was reversed. Maybe I moved it and then enlarged it. Possibility. So that's kind of what we're doing here. We're just trying to describe, either in words or a small little some way to recognize what happened here. So, me looking at example A, in my head, actually the first thing I thought of is actually what I said. I would say that I would take this image and dilate it. Now let's see. This side has a length of 2. This side has a length of 1, 2, 3, 4. So it's twice as big. So if I dilate with a scale factor R equals 2, and we could say about point C, so what that right there would give us is every side would be twice as big. 4, that's 1, 2, 3, 4, 5. So I'd go like 10 up, and it would look something like that. So after I dilate it, the next thing I'd need to do is to translate, to move it into location. So to translate this thing, I'm looking at this point C, I would go down 3, so translate, down 3, and then over 1, 2, 3, 4, 5 to the left. Left 5. I think that would make it into the new image. So here's our original. We enlarged it by doubling it using a scale factor of 2, so everything's twice as big. And then we took that and we moved it down 3 to left 5. 1, 2, 3, 4, 5. And there we go. That gives us this new image. The dilations should be easy to spot. Your image will either be much bigger or smaller than the original. The other ones, well, it's either going to be a rotation, a reflection, or a translation. So in letter A here, I recognize that this original image moved that way, so I say it's a translation. I would also like to mention there is not one correct answer. There are many ways this could have been done. You could have used a scale factor of 2 about and reflect or did the dilation about point B, and then you would go 1, 2, 3, 4, 5 to the left and up 2. Or you could have done the dilation about point A and then went down 3, 1, 2, 4 to the left. I mean, there's all kinds of ways this could have been done. But this one way that I recognized here and I wrote out is one of the transformations that could have taken place to go from the original pre-image to the new image. Letter B. Alright, so the first thing that I see is this to me looks like a rotation. If I would take this image, and I'm looking at this bottom shape here, and if I rotate it this way, it looks like that. That's pretty darn close to what this new image looks like. It's not exactly right, because if you would rotate it, I see. The rotate would take it and it'd be up here. That's where the rotate would take us. It's not quite lined up correctly, but that's what the rotate would do. So if you rotate, let's see, that's clockwise, 90 degrees, so that's one turn clockwise. And then now you have this, what I have in blue here. If we then take that and we translate down 1 unit, boom, we get that. We get our new image. So that's another way it could be done. Again, not saying this is the only way. I'm just saying it's one way that we could accomplish that goal. So rotate it, brings it to here, and then move it down. Move it down 1 unit, brings it to there. I guess in these problems, it's important to be able to recognize if a rotation took place, or a dilation, or a translation, and then being able to, in your head, link the 2 or more of these translations or transformations together to get from one to the other. Here's one that you're going to try. This is, this is one that you're going to try. It says, same thing. You're going to figure out what happened. How do you get from one image to the other? So from the black image to this blue image. Go ahead, pause the video, try it out. When you're ready to continue, hit play, and we'll go through it together. Alright, so first thing I recognize is there is a dilation that took place. I can tell there's a dilation because it's much smaller than it was originally. So I know a dilation took place. But if I just dilate it and do nothing else, it would be, now, freehand, just imagine, like that. So if I dilated it and then rotated it, spun it around, I would get that. Okay, so it's a dilation and a rotation. Now all we need to do is just be more specific. So dilated it how much? Well, let's see here. For me to get from this point here to, I don't know, that point there, this is 1, 2, 3, 4, 5, 6 units tall. Over here, that's this top point here, it's 1, 2, 3 units tall. So it's half the height. So my dilation factor, dilation with a scale factor of r equals half, because it's half the height of the original. About the, where was the scale factor from? Well, I can pick this point, I suppose. It's about the origin. Okay, so we did our dilation. We dilated it with a scale factor of 1/2. We made it half as big, and then shrunk it down towards the origin. Then we would take that new image, which again looks, if you imagine, like that, and then we would rotate it. Let's see, if I rotate, that would be 90. That's no good. That would be 180. Yeah, that's what I want. I want it rotated 180 degrees about the origin again. So there we have it. I kind of acted it out. I showed it a little bit here. That's kind of what I would do. Is I look at it, so there's definitely a dilation, and it looks like a rotation. So I work it out. I figure out the dilation. Well, it's half the size, so the scale factor is a half. I pick a point of dilation to be the origin, the center point here. Then I work on the rotation. Well, the rotation couldn't be 90. It had to be 180 degrees about the origin. So how can you tell if after a sequence of transformations that two shapes are similar or congruent? So what's the difference between similar and congruent? I guess is what this question is really asking. So similar shapes are two shapes that are the same shape but a different size. So similar figures happen if a dilation took place. Congruent figures happen if there was no dilation, if it was just those rigid transformations. So if it was just rigid, if it was just a rotation, a reflection, or a translation, your two images would be congruent. An example would be this letter B. Those two figures are congruent. They're the exact same shape. One is just in a different place than the other. Example A, a dilation happened. So these figures would be similar. Example C, a dilation happened. So those figures would just be similar. So how can you tell after a sequence of transformations that the two shapes are similar or congruent? They're similar if a dilation took place, and they're congruent if there was no dilation. I think that's kind of the simplest terms we can put it. Now, example 2, we're going to construct or similar or congruent figures. So it says, draw the required transformation. Be sure to label your points. Okay. So it has triangle ABC has been reflected across the x-axis, then dilated with a scale factor of 2 about point A. Okay. So example 2. It says construct similar or congruent figures. The directions say to draw the required transformations. Be sure to label your points. Alright. Directions say triangle ABC has been reflected across the x-axis, then dilated with a scale factor of 2 about point A. Alright. So we need to make that figure. So the first thing I'm going to do is I'm going to do the first part. I'm going to reflect it across the x-axis. So it's going to go up there. Same size, same shape, just reflected. So all these points, so this is 1, 2, 3 units away from the x-axis. It's going to be the same just up here. And 2 more higher. And then 1, 2, 3, 4. 1, 2, 3, 4. Is that right? 1, 2, 3, 4. 5. 1, 2, 3, 4, 5. Okay, and we'll break out the line tool. Alright, so that is the first transformation that took place. That is the reflection across the x-axis. Now that's not done. That's reflected across the x-axis. Now we need to dilate that, bigger, smaller, with a scale factor of 2. Everything's going to be 2 times as big about point A. So this is my origin. Everything's going to be getting bigger and smaller from here. These lines are going to be stretched out from this point A. Okay, so let's see here. This line, well, if everything's going to be 2 times bigger, I'm changing to red. If everything's 2 times bigger, 1, 2, 3, 4, 5, 6, which means it needs to be a length of 12 from point A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there is going to be my final destination of that point, which was that point. So that is C prime. So C moved up to here, and then it enlarged, it dilated out to here. Okay, this is my point B. Now this has to become double the size. So I can do this a couple different ways. One way is I can even do this little segment here, the CB. If it's a length of 2 here, if I double it, it should be a length of 4. 1, 2, 3, 4. B prime. The other way would be to look at the directions for me to get from A to B and then just double it. So if I go down 2 over 1, 2, 3, 4, 5, 6, if I double that, I would go down 4 over 12. Still takes me to that spot. And we'll get our line tool to make everything nice and pretty. Make our red. So the red image you see there, that is the final answer. I took my triangle ABC, I reflected it across the x-axis, as you see that was the blue I have under here. Then I took that and dilated it with a scale factor of 2. I made everything twice as big, and that is my answer. So we constructed it. Now, we have a few other side questions. First question says, are these shapes similar or congruent, and how can you tell? Well, these shapes, the original ABC, the original and the new final answer, A prime, B prime, C prime, those two shapes would be similar. And I can tell that because a dilation happened. They are not the same size, so they are similar because a dilation took place. They are proportional to each other. They are similar. They are not the same size. Second part. What is the ratio of the area of A prime, B prime, C prime to A, B, C? Okay, so if we're talking about a ratio, that's a fraction. So the ratio of the area of A prime, B prime, C prime to the area of A, B, C. That's what I want. I want a ratio that has this but with numbers. So that means I'm going to have to go through and actually find the area of these two triangles. All right. Area of my smaller triangle, the original. Well, the area formula for a triangle, area equals 1/2 the base times the height. This triangle has a base of 1, 2, 3, 4, 5, 6, and a height of 2. So if I plug that into my formula and I do some math, 6 times 2 is 12, and half of 12 is 6. So the area of ABC is 6. Now we need the area of A prime, B prime, C prime. Yeah, I can erase most of this because the red line is going to stay. All right. Oopsie, that little guy disappeared. I can fix him. All right, so we need to find the area of this red shape. So the height here, the straight up and down, is 1, 2, 3, 4. I can use the same formula. So the height is 4. The base, I can still use this as the base. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that should give me my area. And let's see, half of 12 is 6. 6 times 4 is 24. So the ratio of A prime, B prime, C prime to the area of ABC is 6 to 24, which can simplify down to 4 over 1. What is the ratio of the area of this to that? 4 over 1. So the area of the new image is 4 times bigger than the area of the old image. Alright, so example 2. Construct similar or congruent figures, where again the directions say to draw the required transformation, be sure to label your points. Alright. Trapezoid ABCD is translated down 5 and right 5. Then ABCD is dilated with a scale factor r equals 1/2 about the origin. Alright. So, start with the first part. So we're going to translate down 5, right 5. So I'm going to take each point and do that. So starting here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And that's just C, so we can label it. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 is D. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 is A. And 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 is B. The drawing the image in here isn't going to help us too much. It might help you just visualize, but this is not the final image. So there's kind of the translation, the first part. Okay, now, then ABCD was dilated with a scale factor of r equals 1/2 about the origin. So I'm dilating about the origin. So all these points are going to zoom in towards the origin with a scale factor of 1/2, which means everything's going to be half as far away. All right, so for me to get from the origin to D, I would go up 2 over 2. Well, half of that would be up 1 over 1. To get to point A, up 2 over 2, half that would be up 1 over 1. To get to letter B, I would go down 2 over 3. Half of that would be down 1 over 1.5, because half of 3 is 1.5, or 1.5. To get from the origin to C, I would go down 2 over 3, which means I go down 1 over 1.5. That's B, C. Those are my primes. Those are my final answer. And there. So the red image, the red shape, is the final image, is our answer for this problem. So I took A, B, C, D, and I translated it down here. I then took that image and I dilated it about the origin with a scale factor of 1/2. So everything is half as big as it was before. And if you measure your sides, AD is 1, 2, 3, 4. Now A prime D prime is 2. BC is 6. 6. Now B prime C prime is 3. Okay, not too shabby. Let's answer some questions. What are the coordinates for point D prime? Okay, well, without actually constructing this, that would probably be a pretty hard question to do. But with the construction, we look up top, we go, oh, That is at point 1, comma 1. How long is side D prime C prime? D prime C prime. I want to give you a chance to think about how you would do this. Take a couple of seconds, pause the video, think about it, maybe like make a little sketch, try something, and then I'm going to show you how I would do it. Alright, so we're trying to find the length of D prime C prime. I'll make it here in green. That's what we're trying to find in this problem. Now, that's kind of a diagonal distance. There's two ways. There's two ways I can think of off the top of my head. I'm sure there's many more. One way is we can use the distance formula. You're trying to find out how long something is in a coordinate plane. The distance would be the square root of x2 minus x1 squared plus y2 minus y1 squared. And we could plug in our points, the points for D prime C prime. D prime is 1, comma 1. C prime is 1.5, negative 1. 1.5, negative 1. And we can plug those values in, and it would give us our answer just fine. Well, let's do it. I'm going to call this my x1, y1, x2, y2. So I'm going to plug in 1.5 minus 1 squared plus negative 1 negative 1, I did it again, no comma, minus 1 squared, and square root it all, and D equals, let's see, that would be 0.5 squared, and that's negative 2 squared. D equals 0.5 squared would be 0.25. Negative 2 squared would be 4. Add those things together, you get 4.25. And finally, square root that thingy. 4.25 square root 2.06. That is the length of side DC. We used the distance formula. Now, the other method that I thought of doing is still using the Pythagorean theorem. Remember, the distance formula is the Pythagorean theorem, just written another way. So I thought about using the Pythagorean theorem, and we can say, well, we know this side, if I draw here and here, we have a little tiny right triangle. This side is length 2. So a squared plus b squared equals c squared. One of the sides was length 2. This side is length 0.5. If you remember, this goes from down to 1 and over 1.5. So this is 0.5. And we need to find the hypotenuse. 0.5 squared equals c squared. And again, this basically just takes us down to that step. And you get 4 plus 0.25. And you get 4.25 equals c squared. You square root both sides. C equals 2.06. A third way I thought of is you could find the length of the side up here in DC. You know this is 1 and that is 4. So using the Pythagorean theorem, you could find the length there and then times it by the scale factor of 1/2, because D prime C prime would be half of DC. That's a third way. All right, some applications. We have here Triangle XYZ has coordinates of x is 3, 4, y is -1, 2, and z is 5, 3. Triangle XYZ was then reflected across the x or the y-axis and dilated with a scale factor of 3 about the origin. What are the coordinates for point x prime? Okay, so a little image might help us, a little model. So 3, 4, yes, 1, 2, 3, 1, 2, 3, 4. That'd be x, and y would be -1, 2, and z would be 1, 2, 3, 4, 5, 1, 2, 3. All right, so that's about what this looks like. So if we reflect it across the y-axis, across this line, the x value is going to go over there, the z value is going to go over here, and the y point is going to come over here. So in my head, we're going to get something like the y, the z, the x. Now, it actually is important that I find what these locations are. So let me take a second here. So if the y value, all it did was move from one side of the y-axis to the other. The height stayed the same. So the coordinate is still going to be something, 2. But instead of being a -1, it's going to be a +1. That's y. The x coordinate, again, the y value stays the same because it's not changing the height, it's just changing the location. So the x coordinate would be, instead of being a +3, would be a -3. And z. Height stays the same. Instead of being a +5 over here, it goes to an x coordinate of -5 over there. Alright, so that gives me the location of all of the points. That's the reflection. Now we need to talk about this dilation that happened. So this dilation with a scale factor of 3 about the origin. So there's the origin. So everything is going to be 3 times farther away than they are right now. So let's see. If I'm only really focusing on the coordinates of the x point, so I don't really care about these other two right now. It's this x point that really makes a difference to me. So for me to get from the origin to the x point, here it is, I would have to go, right now, I would have to go left 3 to -3 and up 4. If I would go and scale factor, dilate with a scale factor of 3, it's going to be 3 times farther away. So I'm going to take both of those dimensions and multiply by 3, which means I'm going to be going 9 units this way and 12 units that way to get my x prime. So my coordinates would be -9 in x and 12 in y. Are we making sense? I hope so. I'm not sure what that's from. So I did my reflection. I kind of made a little sketch of it. I found the locations of the points. The only point I really cared about here was the x coordinate, the x point. Then when I dilated it, I noticed that since it's a dilation with a scale factor of 3, everything's going to be 3 times farther away. So the directions I would use to get from the origin to the x point, I'd go left 3, up 4. So if I 3 times everything, I'd be going left 9, up 12, which would be the coordinate -9, 12. Letter B. Line LM with coordinates L is 2, 5 and M is -1, -1 has been translated using the rule, and there we see the rule. Then L prime M prime was reflected across the x-axis to make line L double prime M double prime. What is the length of L double prime M double prime? Now, I'm going to go off script here a little bit. I want you to try this problem first. I want you to take a little bit of time, think about it, and then do it. Go ahead, pause the video, try it right now. Now, if you did the problem, there's a couple ways that you could get this answer. First off, well, let's do it the long way. So, a little sketch. L is at 2, 5. 1, 2, 3, 4, 5. Over here is L. M is at -1, -1 right here. It says it has been translated using the rule x of 3y goes down. So x is going to go that way, +3 units, and then down 1 unit. Okay, so this point 2, 5 goes 1, 2, 3. So 2, 3, 4, 5, and down 1. So I'd be at the point 5. Oh, not 5. Yeah, 1, 2, 3, 4, 5. I was right. 5, comma, and if I went down 1 here, I'd be at 4. And look, the x unit went up by 3, the y unit went down by 1. That's what this rule shows. M, the x unit, the x coordinate for M would go up by 3, so -1 plus 3 is 2, and the y unit would go down by 1, and -1 minus 1 is -2. So there's the translation. We would then take that and reflect it across the x-axis. So it's going to flip up and down this way. So if you need to, you can make yourself a new little sketch. You're at 5, 4, and you're at, should be -2, negative. Oh no, I was right. I was second guessing myself. At 2, -2. So there's our line. Same thing as that line. And now when we flip everything this way, the x coordinate, the amount that we go sideways, isn't going to change. All we're changing is the up and down. So my L M prime, L double prime will go down here. It's going to be 5, comma, -4. So it's 4 units above the x-axis, which means it's going to go 4 units below the x-axis. That's the reflecting across this x-axis. The M is 2 units below the x-axis. It's reflected 2 units above the x-axis. So this is the location of my L double prime, M double prime. Now, it asks what is the length? Well, we can use the distance formula, and distance equals the square root of x2 minus y2, no, x2 minus x1 squared plus y2 minus y1 squared. Plugging in our values, I'm going to use L as my point 1, so x1, y1, x2, y2 gives me the square root of let's see, we've got x2 is 2, x1 is 5, 2 minus 5, and then 2 minus -4 D equals the square root of 2 minus 5 is negative 3 squared. 2 minus negative 4 is 6 squared. Negative 3 squared is 9. 6 squared is 36. Gives us 45. And clear. 45 square root 6.708. If you want to be detailed about it. So the length of L prime M prime is 6.708 after all of those steps, after doing the translation, doing the reflection, finding the coordinates of the new point, plugging them into the distance formula, and boom. Now, if that's what you did and you got it all right, congratulations, great job. I'm going to show you the easy way. Erase. Now, the easy way is only the easy way because if you took a step and thought about it first, or if you recognize this fact, no dilation took place. All of those transformations that happened were rigid transformations, which means the length of the original line will be the same length as L double prime M double prime. We didn't have to go through and do the reflection and the translation. All we have to do is figure out, well, if the length of this line will be the length of my new line. So the distance formula, again, x2 minus x1 squared plus y2 minus y1 squared. If we plug in the points from here, and I'm going to make this x1, y1, x2, y2, negative 1 minus 2 squared plus negative 1 minus 5 squared. Let's see, that's negative 3 squared plus that's negative 6 squared. D equals square root of 9 plus 36. D equals the square root of 45. And would you look at that, we're going to get that same 6.708 answer. Because it was a rigid transformation. So if you recognize it was a rigid transformation ahead of time, you could have saved yourself a bazillion steps and a ton of work. If you didn't recognize it and you went through and you drew the transformations and hopefully you got it all right, hey, it works too. You just did a little bit more work by maybe not planning enough ahead or not thinking about the problem enough ahead of time. That's all. Letter C. It says quadrilateral PQRS is reflected across the x-axis, then dilated with a scale factor of 3. All right. If PQRS has a perimeter of 22 and an area of 30 centimeters squared, what are the perimeter and area of P prime Q prime R prime S prime? So this is listed as a DOK3, which means it's going to be quite involved. It's going to take some time. It's going to take some steps. Go ahead, pause the video, try it, do as much as you can. If you get stuck, hit play, and then let me catch up in the video and we can talk through some pieces together, and then pause the video again when you get yourself caught up and you understand, and try to work ahead of me again. But go ahead and give it a try right now. Alright, so quadrilateral PQRS is reflected across the x-axis and dilated. Okay, so it has a perimeter of 22 and an area of 30. What are the perimeter and area of this new shape? Well, although it doesn't specifically tell us what shape this is, this PQRS, I have a perimeter and I have an area. Let me think if I can find something that relates to this. Well, to get an area, if I'm talking about a quadrilateral, maybe like a rectangle or a square or a parallelogram, it's base times height or length times width. that would be 6 times 5. So if I had, maybe this is a rectangle or something, and I have 6 times 5, that would give me an area of 30. It could also be maybe 15 times by 2 or 30 times by 1. All of these are possible shapes of rectangles that give me an area of 30. 15 and 2, 30 and 1. Now, if I'm lucky, maybe one of these three would give me a perimeter of 22. Well, let's see. This one gives me a perimeter of 30, 30, 1, 1. That would give me a perimeter of 62. So that's not going to work for us. This would give me a perimeter of 15 and 15. 2 and 2 is 34. That's not going to work for us. This can give me a perimeter of 6 and 6, 5 and 5 is 12, and 10 is 22. So if I use this rectangle that has a length of 5 and a width of 6, that might be a good analogy of what's happening in this problem. Alright, so there's my goal. Okay, so I'm going to use this guy here. And so if I dilate it with a scale factor, well, first off, if I reflect it with across the x-axis, the size and shape is not going to change. That's a rigid transformation, so the perimeter and area would stay the same. So that reflection has no impact on the perimeter or the area. So I can almost ignore it for this problem. But that dilating with a scale factor of 3, that will change everything, because now all of the sides of my shape will be 3 times bigger. So I'm going to take the 6 times by 3 and get 18. The 5 times by 3 and get 15. So my new rectangle after this transformation would be 18 by 15. So if the perimeter of PQ, alright, so what is the perimeter and area of the new shape? P prime, Q prime, R prime, S prime? Well, the area I'd find by doing 18 times by 15, length times width. 15 times 18, 270. The perimeter of any shape you find by adding up the lengths around the outside. So you can take 18 plus 18 plus 15 and 15 and add it together. 18 plus 18 plus 15 plus 15, backspace, plus 15 equals 66. And there we go. The fact that the reflection happened doesn't affect the problem. It doesn't even tell us the coordinates of anything. So we couldn't even do like a model, a sketch. Now I guess you could have made a little sketch of just showing, oh, I have this rectangle over here, and if it's reflected across the x-axis, yeah, then it would be down here now. But that still doesn't help you with solving the problem. The only thing that really had any effect was the dilation and scale factor of 3. And by me kind of doing my pre-planning and using this idea of a rectangle and checking all the different sides to see which size gave me a perimeter of 22 and an area of 30, allowed me to do the problem. That's why this is a DOK3, because it took quite a bit of steps to get from the beginning to the end. So, here is the summary. Let's wrap up this lesson. It says, how does a sequence of transformations create congruent figures? And then how do they make similar figures? Go ahead, pause the video, and answer that question to the best of your ability. And I have, rigid transformations make congruent figures. Those would be the rotations, reflections, and translations. And dilations make similar figures. This has been lesson 3.3. Thank you for watching.